welcome everyone to our, I believe this is the third seminar of our 2024-2025 seminar series of the Technical Committee on Model-Based Optimization for Robotics. Today, for those of you who don't know me, I am one of the co-chairs of our Technical Committee, and here with a few of our other co-chairs and associate co-chairs as well. And today, I have the pleasure to introduce the talk from Prof. Cosimo Della Santina. Prof. Della Santina received his PhD in robotics from University of Pisa and is currently an associate professor at the Technical University of Delft in the Netherlands. Cosimo's research interest is mainly in providing motor intelligence to unconventional robotic systems, especially those involving elastic and soft components. And as a matter of fact, today's talk is titled Motor Intelligence in Soft Robots and Other Unconventional Robotic Systems. And I will leave the floor to Cosimo. So the talk is about 1 hour, including the Q&A time. So at the end of the talk, we'll go over to the questions.
So thanks, you. Can you hear me properly?
Yes.
Good. So yeah, thanks a lot for the kind invitation. Also, very nice introduction. Today I'm going to talk about indeed motor intelligence in and for unconventional robots. With motor intelligence, we mean the capability of generate motion. So I refer to like a very low level intelligence, which is very connected to, of course, control, nonlinear control, but it can be generated in many ways, or studied in many ways. What conventional robots means, we'll probably get more clear later in the presentation. And I will keep this talk relatively high level, but please feel free to ask any technical detail about any technical detail that you wish to know. I'm happy to discuss it. And also, don't wait until the end. If there is something that you want to ask me, please just either turn on your mic or raise your hand, and I'm happy to stop and chat. Okay, so of course, rigid robots, all this. I mean, once we are quite aware of, and these are two, I mean, quite standard ones. But nowadays we have all kind of humanoids and quadrupeds that are doing crazy things and amazing things. This system have been much more precise and reliable, especially in structural environments, that even than humans. But things change when we consider more complex situations, or more precisely, more different kind of movements. And in these cases, we have that animals still largely outperforms robots in performing tasks, in performing motions. You can see here a few examples of that. You have that animals can perform movements that are inherently safe, that are simultaneously precise and compliant. They can be robust to external uncertainties and work into very complex tasks like this harvesting task, and they can generate peak performance. They are much beyond the limits than the actuators that our muscles would let us suspect. So I was build this talk upon what may be seen as a bold statement by someone, or quite established statement from others, but which is that actually, I believe that a large part of this intelligence, this motor intelligence, is generated or can be generated by looking at the musculoskeletal dynamics, so as produced by the body, rather than some explicit computation that goes on in the brain. And again, this is quite a bold statement from some of us, and at the same time, it's maybe not super clear what this means. So to make it a bit more clear, I have a nice video from a research of now of almost 20 years ago. So many of you may already have seen this, but if you have not, um, I, I urge you to look it closely. So first time that I saw this video, I saw a fish swimming in water, which is like trying to do these very complex motions to try to stay more or less in the same position, sustaining this continuous flow, complex flow, because you have this object here that it's creating all kind of turbulence on this side. But after a while, at least I think you start seeing something a bit weird on this fish, but still look normal enough. And then only after you read the paper, you discover this is actually a dead fish. And all these complex motions that you see here that allow the fish to stay where it is, more or less, which is what most fishes in rivers have to do for most of the day, is actually not generated by the brain of any computation in the brain of the fish, but it's just a passive property of the interplay between the mechanics of the fish and the fluid. There are many other examples in nature, and some are even less nice, like this one here. But that basically show the same principle again and again. So the fact that in terms of very low level intelligence or motion generation, a lot in nature is done by the body itself. Today I will talk about these three topics. So starting from these premises, I will discuss about skillful movements without a robotic brain, and then quickly go through some grasping and locomotion, and then a bit more slight more detail on continuum, our work on continuums of the robotics. Let's start from the first. I think that these dead fish examples, as many others, bring us an important question for us of robotics, which is, can we build system that are smart without a brain? So in some other way to put it is, can we go from the dead fish in nature, some kind of zombie robot, and with zombie robot, I mean a robot that can move without computation. Move intelligently. And in order to do so, I guess it kind of makes sense, since natural bodies can do that, to try to replicate or rely on some of the ingredients we can find in nature. In our research, we mostly look at these three different aspects. So the fact that in nature you have distributed actuation, so often muscles do not actuate just one single joint. The fact that you have purposeful under actuation, and maybe most importantly for my own research, the fact that you have a lot of compliance, softness, elasticity into the body. Instead of going very much in details on what all these three means, let me show it with an example. So how you can transfer them into a system. And this is a work that we did now several years ago. And These are self-contained robotic hands with 2 motors and 19 degrees of freedom. And you have here elastic tendons operating in parallel to each joint of this hand, trying to replicate the third ingredient that I shown before. So the fact that you have elasticity in human tendons, and then you have an artificial tendon, which is the one in red here, that goes through the hand and implement the other 2 ingredients, which are distributed actuation and purposeful under actuation. And in order to decide which kind of movements should be generated by this the movement of the motors, we perform a statistical characterization of human motions, and we translated the most common ways for the hand to close via some modeling of the mechanics, blah blah. But what it's important is that in the end we can tune the mechanical properties so that the end could produce any linear combination of these movements. So where the physical intelligence comes into play is when some interaction with the environment happens. And this very simple opening and close behavior that you can see in the box, black box on the right, becomes end up generating a very different final configuration, like something like this, if you can see my camera, or like something like this in the end, depending on the fact that you have an object and that how the object is positioned. And these behaviors are completely an emergent property of the interaction between the hand and the object itself. There is no sensor, no closed loop, at least a computational closed loop. It's all generated as a response of the same feed-forward action. And this, for people, for the ones among of you that know about soft grippers or under-actuated grippers, this is no surprise. And indeed, these are just 3 other examples of works that we have done a bit more recently in my group. And now we are more looking at application in agriculture, and we are not the only ones. So a lot of people are looking into that. But this idea of like just doing 0-1 input to a gripper, and then the mechanics of the gripper will take care of things, something which is very popular. We definitely did not invent it with that hand. But what I was personally struck about when performing this research was instead the capability of the same hand to perform brainless in-hand manipulation, again as a response of a same feed-forward action I will show in a second. And in all these cases, the input is the same, and then you get some very complex pattern of finger movements, and the object is rotated just as a reaction of the mechanics of the system. And this, I would say, it's some physical intelligence in play. And a way to realize that is that if you compare how you would need to do that with a complex robotic hand, the same task, you will end up having to do quite a lot of complex things, like, for example, in this very nice work they use reinforcement learning with full knowledge of object posture and a lot of sensors. And this is the feed-forward input that we generate every time. And these are just a few other examples on how you can use this mechanical intelligent hand. In this case, it's me or some colleague that it's operating this hand either with a joystick or with EEG interface, but sorry, EMG interface. But it's just to show the kind of things that the hand can do mechanically. At some point, we said, okay, hands are cool. We developed over the years several other kind of hands, mechanical intelligence hands able to do several things. Some of grippers, some of them I've shown. But why focusing only on hands? What about more complex stuff? And this is why we started to look into feet. And I will not talk in detail about this robotic foot, but it's based on very similar ideas and very similar technology. What I will do instead is I will show you, I will show an example, actually a video from a follow-up research, which I am not involved, but is so nice. I think it shows very much what this foot is capable of. So this is work of Manuel Catalano, who was also spearheading the research in the other work. But what he did here is that he extended and he basically transformed the robotic foot into a prosthesis. And but the principle again is the same. So what you can see here are all these kind of movements, and especially the one that you probably saw at the beginning, which are like grasping motions that are completely produced passively by the mechanics of the system. And in our papers, in the robotics papers, we have shown that this increases dramatically the region of stability in an even terrain of a inverted pendulum compared to a flat foot. So completely by mechanical properties. More recently, we have then this is really ongoing work. The paper is in press right now. We have thought of pushing this idea even a step further by building a fully passive, fully mechanically intelligent bodies. And here we use similar ideas, this time taking data and trying from dogs running. You can see some snapshots of the data set here. And this is the system that came up. Again, let's look at a video which probably better shows these ideas that are going on. So what you have here is a completely passive. So in the paper we also show an actuated version of this, but what you have in this video is a completely passive walker, which it's a multi degrees of freedom and can generate a variety of different pattern, like more of a let me mute this. And for example, it can adapt via various generating various limit cycle to different velocities. So in a sense, we succeed. Many other people are also succeeding in doing this, or in generating zombie body parts or zombie bodies, meaning a mechanical system that can already solve part of the motor intelligent tasks on a purely mechanical level. And of course, I've shown this as if it was a result of some magic, but clearly there is not always fully understood, but there are sort of control loops, or at least how I like to think about them, going on here on these mechanical systems. They are just implemented mechanically instead of being implemented computationally, but this of course simplify things a lot, and I believe it's quite worth to keep thinking about this and pushing in building more and more intelligent mechanical systems. However, now that you have a mechanically intelligent robot, you may ask yourself, how do I use it? And indeed, thinking about like unless you work in prosthetics, as for example the video of the foot that you have seen, it doesn't make much sense to take this extreme stance. You want to just have no intelligence at all, and actually the larger part of my group research focuses on this topic, so on how you then put back some computational intelligence into the mix, but without ending up losing the mechanical intelligence of the robot. So this brings me to this second part of the talk. And we do that in several contexts. Let me go back here, but mostly, and this is what I'm going to show today, in grasping, in locomotion, and in continuum soft robots, like soft manipulators. With quadrupeds, we look into elastic or soft or articulated soft, or however you want to call them, quadrupeds, and we look at periodic locomotion, meaning steady state behaviors. And what we want to do here is to exploit elasticity. So here you have tendon and springs hidden into the mechanics of these systems. You want to exploit them in order to generate this super efficient locomotion pattern that allow the robots to walk for a very long time, spending a very reduced amount of energy. For example, here we have this quadruped that we developed at DLR. That hides into its mechanics springs, and we are able to exploit these springs to walk for several hours on this treadmill in a completely semi-passive way. But this time we have motors, so we can control the behavior. We conceptualize this periodic locomotion challenge as exciting by means of feedback control loops, nonlinear oscillations or families of nonlinear oscillations that are embedded in or generated by the multi-body dynamics of this system, or this interplay of this multi-body dynamics with elasticity, with potential forces. We are also looking at explosive jumps, and I thought I have only part of a slide that is probably the topic that are most directly related to the TC, because we look at here at either model-based or model-free optimization. And the goal is to generate explosive jumps similar to the frog at the beginning of the talk, by finding way of injecting energy into the springs and then releasing it all together. So this is a Go, as you may recognize, a Go 1 robot from Unit 3, but we end up opening it up and modifying all kind of mechanical parts and also adding some on top, so to have parallel elastic elements in parallel to all joints. So we can store energy in these parallel elastic elements and then release it in order to perform these jumps. But of course, it's quite complex with so many degrees of freedom. And the second topic which we focus on, but I will present it only briefly with this slide, is to understand how we can use mechanical intelligence, robotic hands to do grasping and even manipulation. And most of our works here focus on learning from humans, so using AI, especially imitation learning, to copy human behavior and perform these intelligence motions. The focus here is often to do that from very small data sets, even for just one single demonstration, for example. And this is made possible by a combination of innovation on the imitation learning side, but also the intelligence that it's already embedded in the mechanics. Let's move to the third part of the talk, which is on control of continuum soft robots. And with this, I will present in slightly more detail. And yeah, what we mean with continuum soft robots. With the term soft robot itself is I think a super poorly defined one. And that's why I like to talk about unconventional robots more generally. But the way which I like to define it is any kind of robots where you are embedding purposefully designed compliant elements into the structure. So not just continuums of the robots, but also some of the robots that I've shown before. Any kind of robots that and that follows the third ingredient, so the natural ingredient, so the fact that in animals we have softness and elasticity. But continuums of the robots are nowadays what most people refer if you just talk about soft robotics without any adjective before. And these are inspired by invertebrate animals like an octopus, and they can they have this very complex structure. I mean, here you have plenty of works that have been done in the past decades, but especially the past 15 years, has been again a revive and an explosion of interest in this kind of systems. You can see some of them here. And so you have all kind of robotic platforms around. We developed some ourselves, but what actually interests us the most is to think how you generate intelligence with these systems, and for how extreme and new the system are. In this case, with my group we follow for a good part a very traditional and established way to look at edit, which is to try to express this challenge as a nonlinear control problem. So very trying to see if we can define and then solve the very classic challenges that you have in classic robotics, solved already for many years, most of them, but in this new context. So what from a very high level perspective, what we want to solve are questions like, given a soft manipulator like the one on the left, which includes a body and a set of actuators, like for example tendons in this case, and a desired evolution of the shape of this robot or evolution of some other point like the tip. Answer question like, can this shape evolution be even generated with available actuators? The answer is most of the case no, but you can get maybe some evolution which is close to the one that you desire. And if yes, or at least if you have an evolution which is attainable, how do you generate such evolution in a robust way? By closed loop. And most of the controllers that we aim at developing have this kind of structure. So it's kind of collocated PID plus model-based compensation. So I personally like very much as simple as possible controllers that are very easy to interpret, and they can coded in a few lines in theory. So PID, I think most of us know what it is, and compensation and cancellation. You can, especially of potential forces, you can kind of guess. This is a block scheme of how this looks like, and why I'm presenting this is because in soft robots, and here to explain it properly, I would need probably a couple of hours to go through it. But again, I'm happy to discuss in a bit more detail if you are you're interested. Soft robots are heavily underactuated mechanical systems. So we have to, I mean, you can either go two ways, or you just simplify a lot their dynamics, and we have done this in the past, and you just neglect the passive part, the under actuation. Or if you want really to understand what is going on and really build a robust and effective controller, you have to embrace this under actuation. And a lot of work end up in figuring out that you can rewrite their dynamics as two subsystems. So a subsystem which is directly actuated, by your control input, and a subsystem which is indirectly perturbed by the actuated dynamics. This ending up with this kind of structure allows to define indeed actuated controllers, and this is what we do. So you have a closed loop, for example, with a PID on the actuated dynamics. And then you have some decompensation, which instead is a function of the whole state. And to understand and define these things properly took some work, and that I'm going not to present here. So it's it's below the surface of the water of the iceberg. I will instead show in the style of the rest of the presentation what is above water. So some experiments, some resulting some results that, however, come up after really after starting from trying to establish this theoretical foundation, defining this new algorithm, and then finally we have some experiment to show. But before going to experiment, I'm going to some yeah, let's call it self promotion. So I put online recently this preprint. So I'm where I look at the challenge of closed loop inverse kinematics for structure-like continuum soft robots, but actually also for underactuated gripper humanoid robots and other things where you have a lot of passive degrees of freedom, how you can deal with this challenge and define for in the case of soft robots end up defining the desired shape of the robot to then feed to these low-level controllers that I'm discussing about in this presentation. So this is a huge. I'm showing this slide here because this is a huge topic that has been studied in a simplified setting in soft robotics for many years, and people in soft robotics came up with this cool idea of actuation to task kinematic inversion, and I tried in this paper, in this preprint, to generalize that, but then you realize that this is actually applicable to all kind of system, as I said, and yeah, I cannot think that something similar has not been done in other fields. So this is why I'm asking inputs from you and from other people when I present that are outside soft robotics control, and maybe you can point me out to some interesting reference and work that have tried to or has already addressed a similar challenge in these other fields. So the promise videos. What you have here is metamaterial based soft robot. So it's kind of a weird start for the soft robotic like validation, but this is a very nice system. It was developed within Daniela Ru's group, for example. Yeah, Jeffrey Lipton and Ryan Truby and many others worked on this system. And we have been working on the control of this robot. So this is you have motors on the base here, and then if you move this motor, so you are applying some twist to these elements. Since this is based on a metamaterial that if you twist it extends, you can pair 4 of them so that you can get all this kind of weird with motion and configuration. But then now the challenge is how you close a loop on this motor so to nicely generate these motions. And yeah, this is a scary block scheme that, however, does something very similar what I have shown in the block scheme before. So you have your soft robots, you have some inverse kinematics, but these inverse kinematics really to go from sensors to state. So it's not, yeah, this is like for sensing, while this other inverse kinematics is for control. You have to somehow take into account the underactuated parts, and we do it here. And then we map with this nice decoupled form, which is called collocated form, and then we do basically a PID plus compensation in this setting. Experimental setup looks something like this. So when we do control works with soft robots, we like to rely on reliable sources of information. So we use a motion capture system, but of course there are also many ways in which you can do this proprioceptively. And yeah, this is what you see here, markers, and then this is the robot that I have shown before. And these are the kind of behaviors that you can obtain. So it's a relatively quite sped up video, but I think it shows decently well what is going on. So we want to position the tip of this robot somewhere, and we just follow with closed loop. We are able to do that with, by rotating this base, and you can do nice stuff like nicely drawing the Batman symbol, but also, yeah, other symbols. You have TU Delft and MIT, which are the two institutions that were part of this collaboration. Yeah, more recently we have played with combining this idea together with these people from DCU and combining it with some more some controller that is more relies on deals with interaction with the environment, with control via EEG. So in an EEG cup here. So let me go quick here, but these are the kind of things that you do. You just, the subject is looking at the object, and then it can control the tip in order to perform interaction tasks like pressing this thing. So maybe not too surprising things, but all consider the complexity of things involved. I think it's very, very nice. Yeah. This is another soft robot that we developed to be explicitly underactuated. So this is very clear that this part is passive and this part is actuated via tendons. And it's interesting then to try to do, again, things like positioning the tip despite the this passive element. Yeah, and now we are working on closing like also non-collocated loops that allow to reduce oscillations in this in the tip as well. So other things you may want to do are trajectory tracking, and this is a planet soft robot with many segments, and you define a path in configuration space. And I have not mentioned that, but the configuration in soft robots ends up being some kind of abstract parametrization of the curvature function of the robot or the strain function of the robot, and in I will not go into details once again, but what is important is that you can smartly parameterize the curvature function of this system such that you end up with a structure of the dynamics which looks very much the one that you are used to from classic robotics, and then you just work with these weird distributed joints. But apart from that, things are very similar. And then you can try to perform a trajectory tracking of a shape, as we are doing here. These are other shapes. And what it's nice of, I think, of this experiment here, I always show it. You have these two variables that are connected with the position of the configuration of the base part. So this is a very soft robot. And if you oscillate on the top, what you will get is that you will have a lot of dynamic pairing with the base. And then what you try to do here is to keep the base still, so not move, and withstanding the oscillation on the tip. And you see these balloons bulging with the same frequency of the top, and these are the dynamic coupling that are being compensated by the model-based controller in order to keep these things still. And yeah, you can do Cartesian impedance control to tracing of a trajectory, and you can even do stuff like co-optimizing. Yeah, let me skip this one. Blah blah blah. Yeah, this is another example, I think, of this nice example of doing closed loop control with such a manipulator. This is a tendon-driven soft robot, and you can do closed loop control here to simultaneously have precise positioning of the tip while maintaining compliance. And I'm going fast here because this is another nice video. It's more work in progress, but it's about combining this robot with a wheelchair for doing assistive stuff. So you have here the controller which simultaneously control the robot and the wheelchair in order to allow the subject to move and grasp objects. So this robot now has been the focus of a spin-off that a company that my former PhD student Francesco Stella is pushing forward. So there's a collaboration with Josie Hooks at EPFL, and we are the company is based in Switzerland. And it's if you want to know more, this is our website behind this QR code. Now Francesco is pushing this forward. Going back to academic research, and I looking at the clock, I realized that I don't have time to show all the things I wanted to show, so I will skip a few slides. But something that we have been very interested in recent times is to think about what you can do in the space of moving from this situation, which is the one that I described so far. So you have a software robot, you extract some mathematical model as a prior, and then you deploy this mathematical model in some closed loop controller of the form that I've shown before, but with some nonlinear structure, but closed form structure. And then that's it. So from this situation where the mathematical model is developed by an expert engineer to a situation in which this model is actually, this part is automatized, and this model is extracted by means of learning methods. And of course, given the specific structure of the controllers we play with, it's not possible to just put there any kind of learning strategy, as you could, for example, do if you were using, and has been done by using model predictive control or even model-based reinforcement learning. But you need your model to end up in having a structure that it's compatible with the theories that we developed before. So I have the physical structure that our closed form controller expects. So this is why we look at physics informed learning to learn physics coherent dynamics. And in a nutshell, what you want to do is that you have your mechanical system. You want to collect a data set, of course, and then by supervision, end up with learning the mass matrix, Coriolis terms, potential terms, dissipation, and input matrix. And this is a slightly more detailed structure on how this would this look like. But each one of them are implemented with neural networks. So these allow you end up with a dynamics which is a Lagrangian or Hamiltonian form, which is the one that you like. All this you can play with the structure of this neural network such that they fulfill the properties that you need them to fulfill. And yeah, you end up having this thing that formally are the same that the first model systems that we have shown before. We skip this, and then you can deploy this learned model into a provably stable model-based controller. These allow to do things like closed loop control of both standard and soft robots. As you can see from these videos, actually we can get performance which are of the same level of the off-the-shelf controller that you have in the Franca manipulator, but without any, I mean, completely from data, so without any untuning. But what the control theorist or the content engineer inside me is more happy about is the fact that you can really give guarantees based on the model-based structure of the problem, with based on if the learning is good enough within these boundaries, then you can get this kind of performance, and these are doing some arguments based on robust nonlinear control. There are some twists with respect to what you will need to do with the classic control, but this is fine. So I don't have time to go through, so let me just skip all these very nice things. I'm happy to discuss about maybe next time that we meet. But they are all going to the direction really pushing this idea forward and trying to learn directly from even more abstract data, like for example input outputs from videos using physically consistent learning strategies. And yeah, in summary, I like very much this possibility of combining learning with first principle, because you kind of get the best of the two worlds. So you leverage data to learn from experience and stay adaptable, but also you leverage the structure to learn efficiently and with certified guarantees. And now I have my very last slide, which kind of goes back actually to fully machine learning driven stuff, more into the domain of the things that I've shown before for grasping, or for some of the things connected to locomotion. So and this is an ongoing work which we have put again a preprint online, but this is still research that we are doing. And what you're seeing here is start from the thoughts, or the fact at least itself, that within my group there are people that like to work with rigid robots. I've not shown much about it, but there are people that like to work with this continuum soft robots, and people that like to work on AI. And we thought, is there some way to get the best of these three worlds? So the precision of rigid robots, the embodied intelligence that I started from in this presentation of continuum soft robots, and the capability of adapting to the environment that you will have. Sorry, not to environment, adapting to complex logic situations that you will have from AI and learning from data. So what you see here is a result of that. So just from a single demonstration that is shown to the robot is able to, of course, replay the same task, but also to generalize to different task situation. What you don't see here is the a bit more experiments that we have done now, showing more vast generalizability, not just across a task, but even more interesting across different kind of objects that you play with, or different environment you play with, so that you can really exploit both the embodied intelligence and the computational intelligence. So this is all from my side. Thank you very much for sticking until the end, and I'm open to any question you may have.
Okay, thank you very much, Cosimo, for the talk. I think we can start from the questions. You can either raise your hand or directly unmute yourself, or if you don't feel like doing any of those two, you can also drop your questions in the chat, and I will be monitoring the chat as well. So if you have questions, feel free to come forward with your question.
In the meantime,
while we wait for the audience to think about their questions, maybe we can I can start with one. So this is actually the second time, as you know, that I've attended one of your talks. And I actually don't remember what I asked last time, but I think one thing that I always wonder about soft robots, because I have mainly worked with, let's call them hard, rigid robots versus soft robots. Even though from the definition of soft robots, I think some of my robots are also categorized under the soft category because they have series elastic components. But I think one of the things that I noticed, especially when talking mainly with people who work on mainly rigid robots, is that we're kind of afraid of soft components. Whenever there is anything soft, we're like, oh no, this is gonna cause issues. I was wondering, in, let's say, in the modeling of soft robots versus rigid robots, what's your thought on that, and what's the main maybe difference or similarities that you have, because I think at this time you have worked with both, and you have also mentioned about that inverse kinematics problem you're working on. So just pitching on that thoughts.
Yeah, I mean, thanks for the question. It's there is a lot of unpack in this question, but from the modeling perspective, I think the main difference between rigid robots and continuum soft robots, at least. So the one more octopus like is, in my opinion, the fact that you have with soft robots, you have to accept that the model that you use to do simulations is not or to mechanical analysis is not necessarily the best model or the best solution when you want to generate intelligence, at least if you want to do it in model-based way. And with generate intelligence, I mean everything that goes from really control, but also just analyzing the behavior of the dynamics. And there are like vastly different choices that you will end up doing in formulating the model. Which is just something that has, I mean, I'm a classic roboticist by training. You are just not trained to think about it. I mean, now with AI, we think more about it. Maybe sometimes you may want to have a less precise model, but it's just very fast. That's to simulate, even if for a rigid robot. But in general, we kind of assume that there is one way to model a mechanical system, and that's it. And this is something that you lose with soft robots, because you have to do different choices and different simplification. So this, at least from the modeling side.
Okay, thank you very much. Yeah, I think I mostly agree with the fact that we tend to think only in the traditional way and maybe less open-minded to other approaches. Do we have any questions from the audience? Okay, then maybe in the meantime, I have another. This is a more specific question about one of the works that you have showed. About that. Sorry, I forgot how it's called, but the one where you were drawing the symbols of the TU Delft and MIT.
Yes. So this is.
Yeah, where you had, I think, the BCI interface later on controlling that. I was wondering, in the video I could see, like, this is a purely curiosity question. In the video I could see like a light projection on the back end. I was wondering what is the purpose of that?
Yes. Yeah, this is a quite weird thing we had to do, but was done in order to kind of trying to evaluate. Yeah, let me. Okay, decouple the issues that the subject may have to understand what is the desired position of the tip from the problem itself. So this is just a fancy way we are showing to the subject the tip of the robot should go here, like in the red point, and then this blue thing is just a representation of what the robot is where the robot is, and the white dot is where the tip is at the current time.
Okay,
And
so
yeah, it's just a trick to visualize nicely. I mean, many times in this kind of experiment, you just show something on a screen, and yeah, the two Maxi and Sonal who spearheaded this work had, I think, the nice idea of just showing it overlaid on the real robot.
I see. Okay, nice. I was wondering. Yeah, I thought that maybe it was mainly for them to visualize it better, but I was not sure if it had a secondary purpose.
No, this was indeed the goal. You can see the projector, the projector here.
Okay, thank you. I will just do a last round of call if there's any last questions from the audience. Calling 3, calling 2, 1. Okay, then I will thank you very much for the talk.